This is Physical Chemistry, Part 4, Statistical Thermodynamics, Chapter 31, Ensemble and Molecular Partition Functions, Section 31.1, the Canonical Ensemble. An ensemble is a collection of replicas of a system. There are many kinds of ensembles. The micro-canonical ensemble with constant N, V, E. N is the number of particles, V is the volume, E is the energy. Canonical ensemble with constant N, V, T. T is the temperature. Ground canonical ensemble, constant mu, V, T. Mu is the chemical potential of the particle. Gibbs ensemble, or so-called isobaric isothermal ensemble, with constant N, P, T. Enthalpy ensemble, with constant N, P, H. H is the enthalpy of the replica. Now let's look at the canonical ensemble. A canonical ensemble is a collection of replicas of a system, all having a fixed number of particles, all having the same volume and temperature. It's illustrated here. We have a constant temperature bath, so that all those replicas in this temperature bath have the same temperature. And in each of these replicas, the number of particles is the same. The volume is the same. Now let's look at a numerical example of a canonical ensemble. Again, they have the same temperature, same volume, and same number of particles. So let's say we have a very large number of replicas of a system, and each replica contains 25 particles. Now let's look at the number of microstates associated with these replicas. Over here, I made an Excel spreadsheet. The number of particles is 25, and let's assume these replicas can have 0 epsilon energy, 1 epsilon energy, 2 epsilon, 3 epsilon, etc. And we can calculate the number of microstates associated with the replicas with 0 epsilon energy, 1 epsilon energy, 2 epsilon energy, etc. How do we do that? Here's the equation. You just type up equal sign. FACT is the factorial function. A4, so this is A4 plus $B$1, that's the number of particles, minus 1, so that's the factorial of the number of energy quanta plus the number of particles minus 1, and then divide this by the factorial of the number of energy quanta, and then divided by the factorial of the number of particles minus 1. So over here, this is the number of microstates associated with a replica with 0 energy. What if we have 1 energy quantum? Well, there are 25 different microstates, because you can give this energy quantum to one of these 25 different particles. Now, what if you have 2 energy quanta, 2 epsilon? Well, the number of microstates is 325. Now, why 325? Well, you can give this 2 quanta to the same particle, right? And then you have 25 microstates. Also, you may give this 2 quanta to 2 different particles. So the number of combinations of selecting 2 out of 25 particles is 25 times 24 over 2 factorial. So that's 300. Now remember, we had 25 microstates associated with given 2 energy quanta to the same particle. Therefore, 300 plus 25, you get 325. When you have 3 energy quanta, the calculation gets more complicated because you can give all 3 energy quanta to the same particle. You can give 2 and 1. You can give 1, 1, and 1. So you need to sum up all these microstates. For simplicity, it's easier to just use this equation to calculate the number of microstates. And now this is a canonical ensemble, so every replica has the same temperature as the heat bath. So everything, all replicas have the same temperature. So we can also use the Boltzmann distribution to calculate the relative weight of the replicas. So by using this Boltzmann distribution, you can tell it's more likely to have replicas with 0 energy, less likely to have 1 epsilon, even less likely to have 2 epsilon. However, if you look at the number of microstates, when there is 0 energy, you have the fewest number of microstates. So really, there are 2 factors we need to take into account when calculating the weight of the replicas with different energies. So this weight is the product of this Boltzmann distribution times the number of microstates. So over here, 1 times 1 is 1. How about this? 25 times 0.368, you get 9.2. How about this one? 325 times 1.35 times 10 to the power negative 1. Over here, this is 44. All right? So 3 energy quantum, 2,925 times, this is 0.0498, you get 146 here. So now you can see the number of microstates increases as the energy increases. And this Boltzmann distribution equation decreases as the energy increases. There are 2 factors going in opposite directions. What about the product? The product is the weight of the replicas with these different energies. So you can easily see this number is going up. 1, 9.2, 44, 146, 375, 800, 1,470. It keeps going up. And this weight reaches the maximum here and here. These 2 numbers are very close to each other. So when this 25 particle system has 13 or 14 energy quanta, the weight of that replica with 13 or 14 energy quanta reaches the maximum. So if we plot the number of energy quanta and the weight, it's right here. This is the weight, this is the number of energy quanta. So as energy increases, the weight increases first, and then it reaches the maximum around here, 13 or 14 energy quanta, and then it starts to decrease. As the energy approaches infinity, the weight approaches 0. Now we can also calculate the weight average, the weighted average of energy of those replicas in epsilon. It's 14.55. So what I did is I multiply the energy here by its weight. So these two numbers, I got this number. And then 1 times this number, I get 9.2. And then 2 times this number, I get 88. 3 times this weight, I get 436.88. This is not normalized. So what I did here is I sum up this column and then divide by the sum of the weight. I got 14.55. All right, so that's the weighted average of energy of the replicas. Okay. This is again that Excel graph. As the energy increases, the weight first increases and then reaches maximum around the weighted average, okay, around 14, and then it starts to decrease. I assumed these replicas all have an integer multiple of epsilon, where epsilon is equal to kBt. Well, this is just for the convenience of calculations. So this example shows that the weight of finding a replica with energy E, again this E is an integer multiple of epsilon, so this E reaches the maximum at around the average energy or weighted average energy of all replicas. The weight contains two factors. One, the Boltzmann distribution regarding the total energy of a replica, and 2, the number of microstates inside this replica. When the number of particles is 50, so we can use the same Excel spreadsheet to calculate the weight. You can see the weighted average energy is doubled. It's now 29 epsilon. And again, we have the number of particles here, 50, the number of energy quanta here. We calculate the number of microstates, which increases as the energy of the replica increases. Over here, this is the Boltzmann distribution function. As you can see, this function decreases as the energy of the replica increases. This is the weight. The weight is simply this number times this number. You get this number. And also you can see this number times this number, and then you get this number. So this is weight. And then again, this is just weight times the energy of the replica. The sum of all these numbers in this column divided by the sum of these numbers in this column will give you the weighted average of the energy of these replicas. So it's 29. And also you can see the weight reaches maximum around 29 epsilon here. The weight is proportional to the probability. But here, this weight is not normalized. So we can only say this is proportional to the probability of finding a replica with this amount of energy. In summary, if we have a canonical ensemble, most replicas in this ensemble have an energy very close to the weighted average energy of all replicas. And the average thermodynamic properties of these replicas are very close to the average thermodynamic properties of all replicas. So this statement tells us we can focus on the replicas with an energy very close to the weighted average energy of all replicas and make accurate predictions of the thermodynamic properties of the system.